Okay, so we're trying to work on what this scintillation signal means, and I've artificially set the trigger source of this oscilloscope so high that I'm only seeing the energy for the highest energy gamma rays that are coming out of the detector, and for the cesium-137, 663 keV. So what happens then is I lower the trigger level a little bit, then I'm allowing lower energy pulses to be seen by the oscilloscope. See, we're starting to get this region all filled in here with pulses of other amplitudes. So the question is, what could those other amplitudes possibly be? Cesium-137 is nice to use because it's a monoenergetic gamma ray emitter. It only emits a 663 keV gamma ray. So what are all these other energies in here? The voltages are definitely not all on this highest line here. They're definitely filling in here. So what are those? Well, those are the Compton scattering. So as the photon sort of quote-unquote bounces around through the detector, all kinds of energies are generated due to Compton scattering. As you know, Compton scattering can shift the energy of a gamma ray, and that's exactly what we're seeing here. Not all the gamma rays get directly detected as 663 keV because the Compton scattering can happen. So that's what all these other energies are for here. If I lower the trigger level even more, you see I just keep seeing a whole bunch of pulses of all kinds of differing amplitudes in there, and those are the Compton scattered gamma rays. So this big one right here, this big peak right here, is definitely the 663 keV gamma ray that comes from cesium-137, and all these other ones in here are the Compton scattered gamma rays. Now, it will be a curious point, and I believe you are asked about this in your lab write-up, is it does seem like there is persistent emptiness right in here. There's always sort of like a little dark spot right in here, indicating that there might be some structure to the spectrum that we see that we'll get on a laptop in just a minute. So basically, we see a very strong response at 663, highest energy gamma rays. We see a little bit of a lull in there, and then we see a whole bunch of gamma rays filling in all the way down, seemingly to zero, although not quite. And so this is the core scintillation signal that you see. You're always looking for a bunch of peaks that have a similar shape, but a whole bunch of differing amplitudes just coming in at all different times. So the reason why it sort of flutters like this is just because of that. We don't know when the gamma ray of an energy is going to come in, but they all sort of come in and fill the entire sort of volume in here below, or area rather, below this primary peak in here. And so what I can also do to demonstrate this to you here is run the oscilloscope in the so-called single mode here. So if I just keep pressing single, it just takes one trace. So you see that one, and that one. Now there's a small one right there. There's a little bit larger one. There's a large one again. There's sort of a smaller one in there. So what I'm seeing here, I'm only looking at one pulse at a time coming in. And you can see that a lot of the times, the pulses are very large. Like, you know, like that one right there, very large. That's that highest energy gamma ray, 663 keV. But as I keep hitting single in here, a little bit smaller, a little bit smaller, a little bit smaller. These are the gamma rays that eventually got detected by the detector after they Compton scattered. So there was a very extreme Compton scatter that took that very large gamma ray and reduces energy way down. There's probably a very large scattering angle versus this one here. Maybe not a lot of scattering, if any. There's a very large scattering angle again there. Let's see if we can find an intermediate. There's sort of an intermediate one in there, so probably scattered at a much smaller angle in there, not taking a lot of energy away from the gamma ray. So that's sort of what this signal is here. And so you see one at a time, very instructive here. And if I sort of go back to just running here, that's what the oscilloscope looks like when it samples a signal over and over and over again. So keep that in mind. Basically what you get in scintillation is sort of something that looks like a Gaussian of varying amplitude. That's your core data for scintillation detecting. And I hope you see then that the amplitude of the signal here is proportional to the gamma ray energy that was eventually detected by the detector. That's the core scintillation signal.